Now let's have the rank of a matrix. The rank of a matrix would be basically the dimension of the space. So the row space and the column space of an m by n matrix have the same dimension. They have the same number of leading ones. So row space, so the dimension of the row space is equal to the dimension of the column space. The dimension of the row space or the column space of a matrix is the rank of a matrix, designated by the symbol rank of A. So the rank of A is the number of vectors in the basis or in the row space or the column space of A. So to find the rank of a matrix A below, we convert the matrix B into the row echelon form as shown. So coming from the matrix A, we are going to find the matrix B, which is a row equivalent of the matrix A. So we want to find the row echelon form of matrix A. Now the transformation of this matrix A into its row equivalent to the row echelon form equivalent will be uploaded to the file section of this course. So this matrix A will have a row equivalent, row echelon form equivalent 1, negative 2, 0, 1, 0, 1, 1, negative 1, and 0, 0, 1, 3. The number of non-zero rows is 3, representing the rank of A. So the number of leading ones is the rank of the matrix A. So the number of non-zero rows or the number of leading ones represent the rank of matrix A. The null space of a matrix. If A is an m by n matrix, then the set of all solution of homogeneous system of linear equation AX equal to 0. So you have your matrix A, the augmented matrix A. If you're going to multiply it to the vector of unknown X and equate that to 0, we have homogeneous system. Now, if we have a homogeneous system of linear equation, we can have trivial solution. A system has always a trivial solution, and trivial plus non-trivial solution. So this is another option. So you either have only trivial solution or you can have trivial plus some non-trivial solutions to the equation AX is equal to 0. So the dimension of the null space of A is the nullity of A. The nullity is the dimension of the null space. So null space is n of A, which is the subspace of R raised to n, the solution of R raised to n. So find the null space of the matrix A. So that means you have AX equal to 0. So basically, you can say that you have x1 plus 2x2 minus 2x3 plus x4 equals 0. 3x1 plus 6x2 minus 5x3 plus 4x4 equals 0. And then for the last one, 1x1 plus 2x2 plus 3x4 equal to 0. So what we're going to do is to convert this into its row echelon form. So to find the solution space of the homogeneous system or the null space, we find its row echelon form. So coming from this matrix 1, 2, negative 2, so 1, 2, negative 2, 1, we find the row echelon form, and that would be this matrix. Again, the solution to the row echelon form equivalent will be uploaded in the file section of this course. So, if we are going to write the solution to this one, it would be x1, x2, x3, and x4. So x1 plus 2x2 plus 3x4 equal to 0. We also have x3 plus x4 equals 0. We have a leading one for x1. Leading coefficient, x1 is the leading variable here, and x3 is the leading variable here. We do not have a leading variable for x2 and x4. x2 and x4 did not become a leading variable. So x2 and x4 would be R and S respectively. So in that case, there would be two possible solutions, two possible row echelon form solution. So what would that be? So x1 is equal to negative 2r minus 3s. Negative 2r minus 3s. For x2, it would be r. For x3, it would be negative x4, which is s. And x4 is equal to s. So from this, we have x1 plus 2x2 plus 3x4 equals 0 and x3 plus x4 is equal to 0. We have found out that x1 is equal to negative 2s minus 3t. x2 is equal to s. x3 is equal to negative t. And x4 is equal to positive t. So for in terms of vector, it would be negative 2, 1, 0, 0 for s. And then negative 3, 0, negative 1, 1 for t. So there are two vectors which is part of the solution. So therefore, the nullity of this matrix is 2, with the null space composed of 2, negative 1, 0, 0 and 3, 0, negative 1, 1. So negative 2, 1, 0, 0 and negative 3, 0, negative 1, 1. Negative 3, 0, negative 1, 1 and 2, 1. Oh. It should be, oh, right. It's negative 2, 1, 0, 0. It's correct. Now, for the dimension of the solution space, if A is an m by n matrix of rank R, then the dimension of the solution space of AX is equal to 0 is n minus R. That is, n is equal to rank of A plus nullity of A. So n is the number of elements in the vector space. So if it is a vector r raised to 5, so there would be 5 components on the vector. So n, so the nullity is equal to n minus rank of A. So that would be, in that case, 5 minus rank of A. So as an example, from the given matrix, the matrix is 1, 0, negative 2, 1, 0, 0, negative 1, negative 3, 1, 3, 2, negative 2, negative 1, 1, negative 1, 3, and 0, 3, 9, 0, negative 12. So for this matrix, let us find the rank, the nullity, the subset of the column vectors that form a basis for the column space. So our general solution for this one is to find the row echelon form equivalent. So from the given matrix, we find the row echelon form equivalent by elementary row operation. So after finding the row echelon form equivalent, we can find the number of leading ones that forms a basis for the row space. So that would be or the number of vectors in the column space. So it is just equal. So the rank of A is the number of leading ones. So that is 3. Now, if we are referring to a row space, so that would be 1, 2, 3, 4, 5. So n is equal to 5 in a row space. So 1, 2, 3, 4, 5. So n is equal to 5. So the nullity is equal to 5 minus 3 equal to 2. Now we can also determine the nullity by counting the number of columns that does not have a leading one. So this column has a leading one. This column has a leading one. This does not have a leading one. This have a leading one, and for this last column, no leading one. So the nullity is 2. So that's how we find nullity. We count the number of columns that does not contain the leading one. Now, going back to the row space, the first, the second, and the fourth column vectors are linearly independent, so that the corresponding column vectors of A form a basis for the column space. So the the leading one forms independent vector. So that would be column 1, column 2, and column 4. 1, 2, and 4. So first, second, and fourth column vectors of B are linearly independent. So that would be the first 1, 0, negative 2, 0. The second vector 0, negative 1, negative 1, 3. And the fourth 1, 1, negative 1, 0. These are the vectors that coincide with the leading ones. Thus, these vectors forms a basis for the column space of A.